So let me start by thanking the organizers for this opportunity. I'm going to talk about a project which I've been working on for a while now with Ajit and Shashwat. Shashwat is at Ayuka now. So the title is Constraining Compact Dark Matter Using Non-Observation of Strong Lensing of Gravitational Waves. That's a complicated title, so let's start by breaking it down into the core idea. So our universe is 25% dark matter, stuff which does not interact in any way other than gravity, so far that we know. So if part of this dark matter was made up of compact objects like black holes, it would lens background sources like gravitational waves. So what we will have gravitational lensing of gravitational waves. And since we haven't seen any lensing in LIGO-Virgo events so far, we can constrain the fraction of dark matter in the form of these objects. So in a childish way, you could just say, if you can't see any lensing, if you can't see these signatures in the sky, then there can't be that many lenses. So that's the basic idea. This is not like a radically new idea. You may remember from last year's in-house that Somedi presented similar constraints on dark matter using non-observation of diffraction effects in LIGO-Virgo events. So what they considered was a lens mass range of 10⁻² to 10⁵ solar masses. In this range, the wavelength of gravitational waves that we observe is of the same order as the lenses themselves. So you see diffraction effects on the gravitational waves, which lead to a single distorted image of the original waveform. And we haven't observed it, so they were able to put Bayesian constraints on dark matter in that form. In this work, we go to higher masses, where we have different systematics, different challenges. What we basically see is geometric optics effects instead of diffraction effects, where you see multiple images and each of them is magnified. So the methodology is as follows, just a more concrete description of the basic idea of if you can't see any lensing, there aren't many lenses. You assume that a fraction FDM for a particular mass of dark matter is made up of point masses of mass m. Then you find the expected lensing fraction, the expected fraction of lensed events that we would observe in such a scenario. That is, if we found, say, 100 events in LIGO, then how many of them would be lensed? And since the observed lensing fraction is 0 plus points of fluctuations, we can assign a probability for the true FDM in the universe to be that assumed value using Bayesian analysis. This last part has been done in Somedi's work. All we have to do is substitute for their diffraction effects based lensing fraction with our strong lensing based lensing fraction. The job is to find what is the fraction of events that would be strongly lensed in our universe as a function of FDM. How do we do that? We do it by building a universe on a computer. We fill it with sources of gravitational waves for which the properties are drawn from physically reasonable and also observed properties. For example, the masses of these gravitational wave binaries sources, the binary sources, are distributed according to the observed mass distribution from the LIGO-Virgo analysis. We assign them uniform aligned spins, and their positions are isotropic in the sky, and their distances of proxy for which is the source redshift, ZS, is taken from this paper. And their orientation, these binaries have orientations. We are assuming them to be isotropic in lines of sight. And the next step is to put lenses in front of these binaries. So you basically have binaries at some distances from you. Based on how far they are, there will be a probability of encountering lenses till them. If they are very close, they won't encounter any lenses before reaching you. So there will be a probability of a lens redshift given a source redshift. And this will give you the differential number of lenses at a particular lens redshift. For physically reasonable assumptions like uniform in co-moving density, this P of ZL can be analytically obtained. It is given in this paper. It's basically some factor which is proportional to the fraction of dark matter, the total amount of dark matter, and some cosmological factors. the actual number of lenses that you will encounter will be given by an integral of this. It will basically be the normalization of this PDF. This is what these look like. On the left-hand side is the number of lenses you would encounter as a function of source redshift. It can be pretty high, as you can see. And the probability of where they will occur for a given source redshift is given by this. So once we have put the sources and the lenses in front of them, now we have to find out what will be the effect of these lenses on the actual waveforms, which means we have to solve the problem of strong lensing. So this is a short primer on strong lensing. There are three major effects on a waveform. As I said, there are multiple images. A single unlensed waveform will be seen as multiple images. These will have a certain time delay between them, and they will be magnified with respect to the unlensed image. So when I say that we are going to solve the lensing problem, we are going to find these three things. How many images are there? What is their pairwise time delay? And what are their individual magnifications? So as I said that there are many lenses possible. So the problem is that of multi-plane lensing. You have multiple lenses placed at different planes from you to the source. And in this case, the lens equation, whose solutions give the magnifications, is very complicated. And it has to be done numerically, which is very expensive. As a first approximation, you could just consider the effect of the strongest lens along the path and ignore all of the rest. This has analytical formula, but still it has to be done for many cases, so we do it numerically. So it's a semi-numerical computation. But since you are ignoring a few masses along the way, the final effect will be less than what will be actually there. So the approximate magnifications and time delays will be smaller on average than reality, which means that now since, okay, you get magnifications which amplify the signals that you would observe, which means that you will be able to detect fainter signals because they are now amplified. So if you get higher magnifications, you get higher lensing fractions. And since the reality is 0, which means the constraints will be tighter. Since here you are not seeing those high magnifications, you are going to see approximate constraints which will be less tighter than what they actually will be. Here is a flowchart of how you would actually get the lensing fraction once you have the magnification distributions. So in our simulation, we start with all sources. We put lenses in front of them. If there is at least one lens, those sources are called lens. If there is no lens, they are unlensed. If they are unlensed, you simply take their properties, put them through our detectors, and see if they will ever be detectable. And that will give you the number of unlensed detectable sources. If they are lensed, then there is a small possibility that there could be diffraction effects. We don't want that. We only want multiple images. So we simply discard the other ones. And among the multiple imaged sources, based on their magnifications, we will be able to see at least 2 events through our detectors, or we will only detect 1. So that gives you these 2 other numbers. And then the actual lensing fraction will be defined by this ratio. It's basically the ratio of how many of the events that you have detected are lensed events, or will they be detected as lensed events. So we get this from our simulation for every assumed FDM and lens mass. And this is what it looks like using the strongest lens approximation. And you can see that up to 4% of the total number of events could be lensed. In LIGO Virgo, we have observed 90 events so far. So 4% would have been like, I don't know, 3 or 4. And we have observed 0 lensed events. So which means we can put tight constraints in this region. And you can see that there is something. So how good is this approximation that we are making? Turns out not much. There is this, There is this paper which says that the strong lensing, the single strongest lens approximation actually underestimates the probability of getting high magnifications, more than we expected. It underestimates it more than we expected. So we have to do the numerical computation. We have to write a code which solves this lens equation and gives us the image locations, the magnifications, and time delays. So we did that, and here is an example. I'm showing 3 lenses. Are they visible? Maybe dotted lines. There is a source here, and its images are shown in these patches. So if this was just one lens, you would have seen only 2 images. But here you can clearly see there are many images possible because there is multiple lensing. And then we can basically do this for multiple different configurations of these lenses, their spatial positions, and we can get a distribution of magnifications and time delays. The first column is the magnification of the top image. This is the second most magnified image, and this is the time delay, and these are correlations between them. The orange dots show the strongest lens approximation, and you can see that those distributions are significantly different than what you would get from multiple lensing. So this was actually necessary. Multiple lensing was indeed necessary. Currently, we are stuck at computing the final lensing fractions, the expected lensing fractions, because we are getting some unexpected systematics. Technical, so I won't get into it. But once we get it, we just have to put it through Samadip's pipeline and get the final constraints on FDM. We are at the last step. So let me show the summary. If you can't see any lensing, then there aren't many lenses. Using this fact, we can constrain dark matter in the form of such lenses. So we fill a mock universe with sources and lenses. When we perform strong lensing calculations, multiple lensing is possible. So we have to get numerical solutions, and we are currently stuck at the last step. But approximate constraints are already promising. Thank you.